The next idea is called periodic trends. And these, if you get these are really easy test questions. So here's my, okay, so I want everyone to say back to me. Can you say up and to the right? Say, can you guys repeat back, up and to the right?
Up and to the right.
Okay, and that's the trend. And actually, if you want to be technical, if you have a conflicting, like one element's up and the other one's right, I'm going to use a bad word, up will trump going to the right by at least one or two elements, okay? So up is a bigger difference. So let's look at, here's my bad drawing of the periodic table. Can I draw a periodic table? Is that okay if I? All right, here we go. I'm drawing a periodic table. All right. So as I go up and down, so in the first energy level, there's only one shell, right? In the second energy level, I have two shells. In the third energy level, I have three. When I get way down here, I have 7 shells. So you can see how that's really going to affect the size, right? As I go up, it's going to get smaller. Yeah, that's going to be one of the trends. Okay, so as I go up, I have less shells or energy levels. And that means the nucleus is more exposed also. All right? So what happens as I go to the right? As I go to the right, I get more protons. What's going to happen when I have more proton pluses? So let me show it down here. Maybe this is too or actually no, let's just imagine this is the second period here. I have two shells like this with, say, well, the first element in the second period would be lithium, right? When I get over here to neon, I still have two shells, but they get pulled in really tight, smaller. Because over here I have 10 proton pluses. Over here, let's just imagine lithium, I have 3 protons, right? So if neon has more than 3 times as many protons, it's going to pull all those electrons, shrink. How do I show that? Here, like that. Okay, so big. Let me show that. Let's show that down here. So going across second period. So I'd have a really big 2, right? And then it would get, as I have 3 protons, as I have 5 protons, maybe it gets a little smaller. As I have 7, let's say 8, I don't know. Okay, 8 protons, maybe it gets a little smaller. And then when I get to 10 protons, much smaller, yeah? Does that make sense? So the electrons get pulled in by the protons. So you can think of it like having a bigger force of gravity. You guys think of gravity? I know maybe that's not good to use another scientific concept to talk about a scientific concept. But if you have a big star which has a lot of gravity, the orbitals, that planets will be pulled in closer, right? If you have a star that has weak gravity, not as strong of an attractive force on its planets, the orbits would be wider. And the same thing is true for the electrons. So let's go back. So again, as you go up, you have less shells, nucleus is more exposed. As you go down, you have more shells. As you go across, you get more protons. So the more protons have a stronger pulling force. Okay. And so this is the up and to the right. Yeah? Okay. Let's continue. Okay. So I'm going to draw a smaller periodic table and talk about the different trends. Okay. So Okay, so as I go up and to the right, atoms will have a smaller radius, which means they'll have a smaller volume. They'll also have a higher ionization energy. A higher electron affinity. I'm going to have to define all these in a sec. They will have a higher electronegativity. That's technically in the next chapter, but it follows this trend, so I wanted to mention it. They tend to be more like a non-metal in behavior. They'll tend to gain electrons instead of lose electrons, et cetera, et cetera. Okay. All right. So, and actually in Chem 1A, there's more than these, but all of these things happen as you go up and to the right. As you go down and to the left, so if I go down, I'll write that actually. If I go down left, then I have the opposite. I'm going to have a larger radius, larger volume, comma size, a lower, I'm going to abbreviate it. So ionization energy is IE. Lower electron affinity is abbreviated EA. A lower electronegativity, EN. And you tend to be more like a metal. You tend to lose electrons. Okay? So that's the whole idea. Maybe at this point, this might be a good place to define some of these things. Ionization energy. Abbreviated IE is the energy to, let's not underline that, to energy to remove 1 mole of electrons. So the energy to remove 1 mole of electrons from 1 mole of gaseous atoms. So or ions. So I heat an element up till it's a gas, and then I calculate how much energy does it take to pluck 1 electron off each atom. So we'll look at that. The electron affinity EA is the energy change and this should be said in kilojoules, accompanying the addition of 1 mole of electrons to 1 mole of gaseous atoms or ions. One other thing to say about electron affinity is it's kind of a rough trend. It's not as beautiful as some of the other ones, like the volume. Rough trend. Okay. But again, they take 1 mole of atoms, they heat them up till they're a gas, and then they add electrons and they look at the energy change. And even though this one's in the next chapter, I want to define it. The electronegativity En is the relative, and how they measure this is, I'm not sure exactly, but use this chart for eons, is the relative ability of an atom to attract shared electrons. So meaning if I have electrons in a bond, so like hydrogen and chlorine, which atom has a stronger pull? Let's see if I can pull question mark. And the last thing to say about electronegativity is noble gases are excluded because they don't tend to want to make bonds and gain electrons. So they're excluded from this chart. So electron configurations are related to the following properties: relative reactivity, how reactive an atom is, right? Ionization energy, the tendency to lose electrons. The atomic radii, which also, the radius is exactly proportional to the size, right? The volume, if an atom is a sphere, you guys remember from geometry, the formula for the volume of a sphere, it's 4/3 pi r cubed. A small change in a radius equals a big change in a size. We talked about the activity series. The most reactive metals are the most down and to the left on the periodic table. The least reactive metals are the most up and to the right, essentially. So we see that the most active metals are those in the 1A and the 2A, really far to the left on the periodic table. The more active the metal, the more easily it loses electrons. So remember, if it was a competition between two metals, the calcium would force something lower than it to gain its electrons. Calcium would give its electrons to zinc, and zinc would have to take it. Or zinc would give its electrons to nickel, and nickel would have to take it, and so on. All right, so that chemical reactivity. And this is just the reactivity of metals. There's a corresponding activity series that we didn't cover that has to do with the halogens. So the more up and the right, fluorine would be more reactive than chlorine, and chlorine would be more reactive than bromine, right, in a similar style and fashion. Okay, so alkali metals form +1 ions since they only have one valence electron. So you also see these patterns too, right? There's patterns of reactivity. All of the 1A metals form a 2-to-1 ratio with oxide, right? Li2O, Na2O, whereas all alkaline earth form a 1-to-1 ratio, MgO, CaO, SrO. So the patterns of the ionic compounds they form, it's very predictable. All of the 1A metals react very violently with water. They actually catch on fire in water. This is showing the idea as you go down, these are all 1A, right? Lithium is in the second period, sodium's in the third, hydrogen fourth, rubidium fifth, cesium sixth. As you go down, they get more reactive. If you look at cesium, it's basically exploding when it hits the water. Whereas when sodium hits the water, it's going to think for a while, and then it's going to catch on fire. And then sodium's going to just kind of fizzle, not as reactive. I mean, they all react quite vigorously with water, but that trend, as you go down, it becomes even more pronounced. But all 1A metals react with water to form a metal hydroxide and hydrogen. And then the hydrogen gas, because so much energy is being released, the hydrogen gas reacts with oxygen. You get this violent reaction. Okay. We mentioned ionization energy, and we wrote it down. Ionization energy is a measure of the energy required to remove a valence electron from a gaseous atom, and specifically 1 mole from 1 mole. I take an atom and put it in the gas state, and then measure the energy change when it loses an electron. Metals will have low ionization energy, and non-metals will have higher ionization energies. And that follows that same trend. So this is actually, if you guys can see this graph, this is showing ionization energy, right? Cesium has the lowest ionization energy on the periodic table. Helium has the highest, right? Because it's the atom that is the most up and to the right. So again, as I go up the periodic table, there's less shells. So if there's less shells, again, up here, there's less shells. One shell, two shells, right? And so if there's only one or two shells, then the protons in the nucleus are more exposed. The electrons will feel the pull of those protons with more power. As I go across the periodic table, I get more protons. So if I look from lithium going up, it looks like almost like a ladder. Now there's some places where I go down. Like if you look lithium, I go up to beryllium. I slightly down to boron, but then I go up to carbon, up to nitrogen, slightly down. So it's a trend. It's not a perfect trend. The trend going across is a little jaggedy. If you look at the trend going up, look at the purple. So it's up, 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 up. So going up is basically a perfect trend. Non-metals that have very high ionization energies are never going to lose electrons. It's going to be not in nature, not in a natural reaction. It would take some weird artificial process to pluck an electron away from fluorine or helium, right? But the metals down here with really low ionization energies can lose electrons in nature. They can get stolen by something that has a very strong attraction. And if you look at like selenium, arsenic, silicon, though tellurium, they basically have an intermediate ionization energy. The differences between being a metal and a non-metal and a metalloid is, you know, basically a difference in ionization energy and some other of these periodic trends that we'll see. So ionization energy increases as you go up and to the right, right? So again, it has to do with the shell size. As you go up, you have less shells. The outer electrons fill the pull of the nucleus more. As you go across, the shell shrinks and gets smaller, right? And that's the basic idea going on here. Let's continue. So for these, you just have to look at the periodic table. Magnesium and calcium. Well, which one's more up and to the right? Calcium and magnesium.
Magnesium?
Magnesium, yeah, they're both in the 2A. Magnesium's higher, so magnesium's going to have a higher ionization energy. These are really easy test questions if you get the trend. If you can just say up and to the right, oxygen or fluorine. Aha. So, fluorine. Yeah, why did he say fluorine? That's correct answer. So magnesium is up. Fluorine is to the right. It has more protons, right? Magnesium is up. It has less shells. So the electrons in those shells are held more tightly. Ah, silicon or fluorine? Which one's going to be? Fluorine. Fluorine. Well, fluorine is both up and to the right, yeah? Ionization energy decreases as you go down and to the left. You have the opposite trend. Why is cesium so explosive when it reacts with water? Because it's really easy to pluck off an electron. It doesn't take a lot of energy to break that electron bond. And when you form these products, you give off a lot of energy. It's a really interesting reaction. There's also an idea of what they call successive ionization energies. The first ionization energy, IE1, IE1 equals first IE. IE2 equals second ionization energy. So in general, so So the first ionization energy would be removing the first electron. The first ionization energy was around 700 kilojoules per mole. So that's the energy to remove the first electron. And so magnesium ion, losing a second electron, going to magnesium 2+, well, that takes about twice as much energy to remove that second electron. Why would it take more energy to remove the second electron? What's going on? Well, magnesium has 12 protons. So as I lose electrons, the electrons I have left are held more tightly, right?
Yeah.
So it doubles. It doubles. But now let's look at the third ionization energy. What happened with the third? So now I have magnesium 2+, and I'm going to remove a third electron and go to magnesium 3+. Now, does magnesium 3+ exist in nature? What's the normal ion of magnesium?
Mg2+.
Magnesium 2+. So look, there's a huge energy jump. It's 7,733 kilojoules. So if we're going from 1,400 to 17, that's a five-fold jump. Why 5 times jump for IE3? What's going on? Why is it such a big jump? Anybody think about that? So we're removing core electrons. And so when we remove core electrons, right, magnesium 2+ has got the electron configuration of neon. When I go to magnesium 3+, I'm removing those core electrons, and that's very costly. They're super stable. So this is showing the pattern, actually. Lithium has low first ionization energy, then there's a big jump. So lithium is 2s1. Once I remove the second electron, that takes a lot of energy. Beryllium has a big jump at the third electron because those are removing core electrons. The core electrons are shown in gray. You know, carbon, I can remove the first 4 electrons, then the fifth one takes a lot of energy. There's a huge jump, and it has to do with removing core electrons, okay? The atomic size is usually reported as the atomic radius, 1/2 the distance between the centers of 2 bonded atoms, right? So if I have chlorine-chlorine, this distance between the halfway in between the 2 nuclei would be reported as atomic size. And that shrinks as you go up and to the right. Okay, so as we go up and to the right, we get smaller. This is a really nice trend. It's observed almost perfectly. And it increases as I go down and to the left.